My name is Brice and I work at Vibratech. And as we are in a session about weld and joint, I guess I have to choose one of the subjects, so I've chosen rail joint. Before I start to speak further about the subject, I must mention that we started the work for SNCF, and we have made further investigation after the study we performed for SNCF, and this research I'm presenting now is about this investigation. So rail joints, well, few words about rail joints. They generate high level of contact force, and regarding simulations, this means that we need high frequency content, so you need to have computational effort. And also the geometry is complex, so you need to account for really precise geometry model. So this pushed us to use 3D modeling and finite element. Three possible configuration of rail joints. First one is level rails, so the two rails are the same level and the wheel is crossing the joints. The second one is a step-up joint, and the last one is step-down joint. So we have performed computation on three of them, and we will only focus on the step-up joint in this presentation. The parameters are the height of the joints, which is 1 millimeters, and the size of the gap, which is 15 millimeters in this case. Okay, so the purpose of the studies at the beginning is to obtain the rail contact force in order to use this contact force as an input for fatigue prediction and fissuration into the bolt component and the joints component. In the presentation, I will go through two items. The first one is a benchmark that we have done between 3D finite element model, which is the initial model we use for SNCF, and a simplified approach with multi-body and 1D beams in order to be able to perform parametric variation, because 3D models is quite expensive in terms of computational time. The second one is, the second item is the rail plastic behavior. We have included the rail plastic behavior in order to see the influence on contact force, because on the previous computation we only used elastic material. Let's go through a presentation of the model. So the first one is the finite element model, so the 3D one. We use a software, commercial software, which is called MARC. It performs nonlinear analysis in time domain computation. We have a rolling wheel set at 160 kilometers per hour. And we use a segment-to-segment contact research algorithm, which is set up into MARC. So you can see the joints here with the bolts and the sleeper spacing as well. So we have included different sleepers in between below the rail joint. Regarding the contact zone, what we do is we use a finer mesh on the circumference of the wheel, and we also use a finer mesh at the rail joint. For the plasticity, we have included plasticity using a Schabosch description. So we based our model on previous research by Fischer and Schleintzer. This model is included into the MARC model in 3D. For the benchmark, we are using a model which is based on a software which is called Voco and is developed by French IFSTAR, which is the French research institute. So the model is constituted of a wheel set, which is a rigid model, and a rail with flexible model. So the wheel set is a rigid wheel, rigid axle, and suspended mass. In between the wheel and the rail, we have contact, and the joint is described by a relative prescribed displacement, and so we input the wheel center trajectory in the spring, which represents a Hertzian contact. Okay, results. So let's go through the results of the benchmark between VOCO and the 3D finite element model. So here you see the vertical contact force as a function of the time during the computation, and the rail joint is here. So what do you see? What you see is you have several steps, several items. The first one is the static load. Before you enter the joint, you have just a static load. And when you enter the joint, the impact on the rail joint will give you what we call the P1 peak, which is related to the contact and the mass of the wheel and rail, which are moving on the spring, on the Hertzian spring, on the contact spring. So this gives you the maximum of the contact force. Then you have oscillations at about 900 Hertz, which is, well, the same oscillation of the first peak, which is still due to the resonance of rail mass and Hertzian stiffness. In this case, you have a loss of contact here because, well, you can see the static force, the force is going down to 0. And afterwards, you have a rebound corresponding to the P2 peak, which is the axial mass bouncing on rail stiffness at about 80 Hertz. Well, you can see the difference between VOCO in blue, so the simplified approach, compared to the 3D model. So in VOCO, you have much more oscillation, which are due to the simplification of the Hertzian spring, and the Hertzian spring is in parallel with a damper, and the setup of this damper and the stiffness will give you this oscillation. So you need to set up the parameters of the model to be able to capture correctly this part. Okay, and then in the end you have kind of the same shape for the P2 peak. And you also have a small difference at the P1 peak. Results for rail plastic behavior. So this has been done only with the 3D model. And we have compared, so it's still the same graph, vertical contact force as a function of time. And you have a result of elastic in black and plastic in red. And you can see, as expected, that the peak is reduced using rail plasticity. Well, and well, quantifying it, you have a reduction of about 20%. Well, you can see here the residual stress after wheel passage. We have done much more analysis than what I'm presenting here in the study, and I have included that into the paper. So if you want, you can read it in more detail. Okay. Well, just an animation. I think you can see here the contact patch. So when it goes onto the rail joint, then it goes further, and you can see the residual stress here. And here it's the loss of contact, and it will come back somewhere here. So then you have the P2 peak here after the resonance. Okay. Well, this leads to my conclusion. So the first things we have done is to include rail plasticity and see the effect. And well, we have noticed that in this case it reduces by almost 20% the contact peak force. One of the further investigation that we will make is also to include the wheel plasticity. For the moment, it hasn't been done. Just to give you an order of magnitude, one computation takes about 24 hours on our computers. So That's why we have done this second step, so the benchmark, in order to do parametric variation in the future work. And we have come to a conclusion that the simplify approach can be used for parametric variation, but you need to set up some parameters, and that's what we have done using a comparison between 3D and 1D. Perspective, as I said, is well, to include the wheel plasticity, and also what we are looking at in the next step is to repeat the wheel passages in order to calculate the plastic deformation after cyclic deformation, cyclic repeated load. Well, all of that is part of development that we have at Vibratech. We are trying to have the best tools. Historically, we are more related to design, and we are going into operation and maintenance. So we need to have tools to be able to predict what will happen in operation, and go back to design, improve the design, and this is an infinite loop here, as I illustrated. So design and maintenance, design and operation are always connected, and you can gain experience from one and use this experience to improve the other one. And with this view, we are looking at fatigue, wear, but also acoustics and vibration comfort. I think I have one more slide. Yeah. Well, thank you for your attention.